Hello everyone. This is Dr. Captain K. Sujata, Professor of Mathematics, St. Joseph's College for Women, Autonomous, Visakhapatnam. In this session, I am going to discuss problems on Cayley-Hamilton theorem. Now these are my details. Dr. Captain K. Sujata, my name. If any doubts after this session, you can contact through my email ID. Any doubts, directly you can send a mail to me, then immediately I will respond. These are the course outcomes. After successful completion of this course, the student will be able to know and apply the principles of linear algebra, know vocabulary, notation and operations for matrices and vectors, find the characteristic equation, characteristic values and characteristic vectors of the matrix, apply Cayley-Hamilton theorem to problems for finding the inverse of a matrix and higher powers of matrices without using routine method. Routine method is for finding the A inverse. A inverse is equal to adjoint A by det A if det A is not equal to 0. Without using that method, if we apply the Cayley-Hamilton theorem, directly we can do the problem for finding the A inverse. Right? In the previous sessions, for what we discussed, we have discussed following topics. There's some definitions on characteristic matrix, that is A minus lambda I. No, characteristic polynomial, determinant of A minus lambda I. Characteristic equation, that A minus lambda I is equal to 0. Characteristic root in the characteristic equation, lambda is called characteristic root, and characteristic vector. For every characteristic root, there exists a characteristic vector, corresponding characteristic vector. There is a non-zero vector x, such that lambda ax is equal to lambda x. There x we call it as a characteristic vector, right, under the matrices. Some theorems on characteristic root and characteristic vectors of square matrix and linear operator we define. And also these are all definition under linear operator. These are all definitions on matrices we are defined. And in the same way we can define under linear operator also. Linear operator, under linear operator, the characteristic equation, the characteristic vector is T of alpha is equal to Ci. T of alpha is equal to Ci alpha A, whereas alpha, T of alpha is equal to C alpha, whereas alpha is a characteristic vector and C is a characteristic root under the linear operator. Now coming to the, after that we have discussed in the second video, procedure to find the eigenvalues and eigenvectors of the matrix. Now after that we have discussed problems on eigenvalues and eigenvectors, some problems we have done. Then also some identities and eigenvalues and eigenvectors in the last before video, and that is the third video. We have discussed some identities on eigenvalues and eigenvectors of the square matrix. And in the last video, we have discussed Cayley-Hamilton theorem on square matrix as well as a linear operator. Right? No, this is a statement because we need the statement of the, if you recollect the statement of the Cayley-Hamilton theorem, easily you can do the problems on Cayley-Hamilton theorem. Every square matrix satisfies its characteristic equation. This is a statement of the Cayley-Hamilton theorem. Right, next to find the characteristic equation of the matrix A 1 0 0 1 0 2 0 2 1 2 0 3 and verify that it is satisfied by A and hence find its inverse. Right, so this is a matrix 1 0 1 0 2 0 2 1 2 0 3. Right, now after that what we want to find out, first of all we have to find out the characteristic equation. So after getting the characteristic equation, what we want to find out, verify that it is satisfied by A, means that is nothing but characteristic Cayley-Hamilton theorem. Verify that it is satisfied by A, that is every square matrix satisfies its characteristic equation, right, and hence find its inverse, means use the Cayley-Hamilton theorem only. We have to find out the inverse, not in the routine method. Right, so first of all, first I will explain how to get. Already we discussed on characteristic equation. Again I want to explain once how to find out the characteristic equation. Now what is the matrix here? A is given. A is equal to 102. Now here A is equal to 102, 021, 021, 203. Right? So take the matrix as that one. Go to screen, white screen. Right? So here what is the matrix is given? A is equal to 102. No, A is equal to 102, 021, 023, 203, right? So this is a matrix is given. Now what we want to find out, first thing is, first to find out characteristic equation. Characteristic equation, that is meant by, what is the characteristic equation? Determinant of A minus lambda I is equal to 0. This is a characteristic equation. Means that implies, what is the determinant of A minus lambda I? 1 minus lambda. Whereas what is the unit matrix? Because this given matrix is 3 by 3, automatically unit matrix is also in the form of 3 by 3, 1 0 0 0 1 0 0 0 1. This is a unit matrix, right? So from this, what is a lambda I? Lambda I can be written as lambda 0 0 0 lambda 0 0 0 lambda, right? From this. Now if we substitute, then find out the characteristic equation A minus lambda I. So 1 minus lambda 0 2 0 2 1, 2 minus lambda here. So diagonal elements we have to subtract with the lambda. 2 0 3 minus lambda. This is a characteristic equation equate to 0. Polynomial characteristic polynomial equate to 0. Expand this determinant. This can be written as 1 minus lambda into 2 minus lambda into 3 minus lambda minus 0, minus 0, minus 0. So this in minus this one, okay? Then after that, minus 0 into this is over. This is closed. 1 minus lambda into this term is over. After that, minus 0 into, so here minus 0 into 0. Anyhow, 0 is multiplied by anything is nothing but 0, right? So actually this is a minus 2, only minus 2. Because just I want to, so whatever this element, just to see how to multiply. 0 into 3 minus lambda minus 1 into 2, right? So that is minus 2. Plus 2 into 0 into 0, 0 minus minus of 2 into 2 minus lambda. 2 into 2 minus lambda is equal to 0, right? Is equal to 0. So this is the expansion of this determinant, right? Now after that we will get so expand this, we'll get the one characteristic equation in terms of the lambda cube and so on. We'll get lambda coefficient of, in terms of the lambda square, in terms of the lambda plus a constant term, whatever the sum is equal to 0. Right? So finally, we will get one characteristic equation of third degree in lambda we will get. That coefficient we will get after simplification, we will get something. Right? So what we want to show next thing is this characteristic equation satisfied by A, by the square matrix A. So we have to show that, what we want to show, A cube plus whatever the coefficient A square plus no next some coefficient into A. In place of lambda we have to take some constant is equal to 0, right? So whatever the plus or minus, so these are the satisfied by A, characteristic equation satisfied by A, right? Now after that what we want to take, right, this one, right? So here now from that, after the expansion we got one equation, characteristic equation, right? Now next what we want to show, prove that A satisfies the given characteristic equation, that is in place of lambda we have to take it. This is a statement we want to prove, right? So means one by one you calculate. So this is a this value we want to prove it is a 0 matrix. Now first we need A square. First we need A square, you calculate A square. A square is nothing but A into A. Means multiplied A into A again. Means how to calculate the multiplication of the two matrices? 1 into 0. First row with the first column. First element. Similarly, first row, second element with the first column. first row, third element with the first column only. First column only. 1 into 1, 1. 0 into 0, 0. 2 into 2, 4. Right? Similarly, first row, second column will get this. First row, 1 into 0, 0. 0, 0. 0 into 2, 0. 2 into 0, 0. So first row, first column, again first row, second column, again first row, third column, you have to multiply like this. So from that we'll get the first row, right? Similarly, second row, first column, second row, second column, second row, third column. We'll get like this. Similarly, third row, first column, third row, second column, third row, third column, right? So these are the three elements we'll get, right? This is the first row, second row, third row. Simplify that, we'll get a square matrix. Similarly, find out a cube. A cube can be written as a square into a. Already we got a square here. A square into a, that is again multiply these two matrices. First row 5 into 1, 0 into 0, 8 into 2. That is the first element of the first row. And 5 into 0, 0 into 2, 8 into 0, again 0. 5 into 2, 5 into 2, 0 into 1, 8 into 3, third row, first row, third row elements, right? So these are the elements. So after simplification, we'll get this is a matrix of A cube, right? Then after that, substitute these values in LHS of the required condition, right? So that is this one. So simplify that. We have to prove this is a matrix as we want to prove that this is a value as zero matrix. Okay. Now after that we have to find out the A inverse. How to get the A inverse? Multiply the characteristic equation with the A inverse. Characteristic equation with satisfied by A, no, that Cayley-Hamilton statement with A inverse. So what we'll get? So multiply this equation with A inverse throughout. So we'll get this one. Then after that, from this we can calculate the A inverse. So 2A inverse is equal to minus A square plus 6A minus 7i. So I'll explain that one easily. So this is the given equation we got it, no, A cube minus 6A square plus 7A plus 2i is equal to 0. So right, so if we take this one, so we multiply this equation with the throughout with the A inverse. So if we multiply with the A inverse, this first term becomes A square. This is A, this is I. A inverse into A is nothing but I, right? I into A inverse is nothing but A inverse. From this, we can find out the A inverse. A inverse is equal to remaining terms, right? So from that, this is the term multiply with the A inverse means that characteristic Cayley-Hamilton theorem statement will get this equation, right? Now after that, then 2A inverse is equal to remaining terms minus A square plus 6A minus 7i, right? Then after that, A inverse can be written as half into this one. Then substitute, though we know A square, we know 6A, we know 7A. Then simplify that, we'll get the A inverse matrix. Okay. Now coming to the second one, show that the matrix A satisfies the Cayley-Hamilton theorem. Same. Satisfies the Cayley-Hamilton theorem means, first of all, we have to find out the characteristic equation, that is determinant of A minus lambda is equal to 0. Simplify that, we'll get the characteristic equation as lambda cube plus lambda into A square minus this is a characteristic equation, lambda cube plus lambda into A square plus B square plus C square is equal to 0. Now from the Cayley-Hamilton theorem, A satisfies the, we want to prove, we want to verify the Cayley-Hamilton theorem here. Means A cube plus lambda into A square plus B square plus C square, we want to show it is a zero matrix. Right? Now one by one, similar to the previous problem, we calculate A square, after that A cube, then substitute in LHS, we'll get the RHS as zero matrix. So simplify that, we'll get RHS as zero matrix. Therefore, A satisfies the characteristic theorem, Cayley-Hamilton theorem. Right? Now coming to the next problem, if A is equal to 2 by 2 matrix is given, then express this is a value polynomial as a linear polynomial in A. Is a linear polynomial in A by using Cayley-Hamilton theorem, right? Now here also use for getting the Cayley-Hamilton theorem, we have to find out the characteristic equation. So find out the characteristic equation. We'll get 3 minus lambda into 2 minus lambda plus 1 is equal to 0. Now further simplify this one. Then we'll get the characteristic equation as lambda square minus 5 lambda plus lambda is equal to 0. Now by Cayley-Hamilton theorem, lambda is satisfied with the A. That is the characteristic equation satisfied by A. Means in place of lambda, take a square minus 5a plus 7i is equal to 0. Right? Now, next we are going to, we want to prove that which condition we have to prove. So this is a statement. This is a polynomial. We have to convert to then express this as a linear polynomial. Means we have to simplify this as much as possible. Right? Using the Cayley-Hamilton theorem. Right? So that's why here, so we got this condition. From that, we have to use this condition in this. Now, write down this equation as, write down this polynomial, this expression otherwise. 2 into a power 5 minus 3 into a power 4 plus a square minus 4i. This can be written as, right? So we have to split the term in terms of the this, in term, because we can substitute this value as 0, no? That's why we are converting this into like this. Right? So plus remaining terms, this into this, after multiply these two, and if we add these these two will get this one. So this into this, you have to remember only. That is, we have to convert this into in the form of like this, plus remaining terms. Now we are replacing this is a value here. Right? Remaining, so final linear polynomial is, this can be expressed as 138a minus 403i, right? Same, similar to the next problem also, similar to previous one. Find the characteristic roots of A. So first of all, we have to characteristic roots also, extra condition, and verify Cayley-Hamilton theorem for this matrix. Find the inverse of the matrix A, and also express this is in the form of the linear polynomial in A, right? So this is a 2 by 2 matrix. So 1, 4, 2, 3. So how to get the characteristic equation? A minus lambda I is, what is the characteristic equation? A minus lambda I is equal to 0, right? So from that, A minus lambda I means you write down. Then after that, simplify, you'll get the characteristic equation. 1, 4, 2, 3. Otherwise, I will take the board and I'll explain. So take the pen and little bit screen whiteboard, you take it. Just explain what is 4312. No, already explained about the characteristic equation. Here also A is given in the form of the 2 by 2. No, 1423. 1423. Then what is the characteristic equation? Characteristic equation can be written as determinant of A minus lambda I is equal to 0. Right? So from this, what is the characteristic equation? 1 minus lambda, 4, 2, 3 minus lambda is equal to 0, right? Because I is 2 by 2 unit matrix. So this can be written as 1 minus lambda into 3 minus lambda minus 8 is equal to 0. So this can be written as 3, 1 into 3 minus lambda minus 3 lambda plus lambda square minus 8 is equal to 0. Right? From this lambda square minus 4 lambda plus minus 5 is equal to 0. Right? So here what are the factors? 5 into 1. So that is minus 5 plus 1. Minus 5 plus 1 is minus 4. Minus 5 into 1 is minus 5. Right? This can be written as lambda minus 5. What are the characteristic roots? Lambda minus 5 and lambda plus 1. Then the characteristic roots are lambda is equal to 5 and lambda is equal to minus 1. These are the characteristic roots. This is a characteristic equation. Lambda square minus 4 lambda minus 5 is equal to 0 is a characteristic equation. From that, these are the characteristic roots. After getting the characteristic root, what they are finding, what we want to find out, it is also verified by Cayley-Hamilton theorem. Means what we want to show for verification of the Cayley-Hamilton theorem, what we want to show, a square minus 4a minus 5i is equal to 0. We want to prove this one. So first of all, find out a square. How to get a square? 1423 into 1423. 1, 4, 2, 3, right? So multiply these two. What will get? 1 into 1, 1. 1 first row, first column. 1 into 1, 4 into 2, 8. That is the first element. 1 into 4, 4. 1 into 4, 4. 4 into 3, 12. Right? 2 into 2, 2. 2 into 2, 2 into 1, 1. 2 into 1, 2. 3 into 2, 6. Right? And 2 into 4, 8. 2 into 4, 8. 3 into 3, 9. So this is a matrix of A square. So this can be written as 9, 16, 8, 16 plus 7, 17. Right? So this is a matrix of A square. Now after that, 4A write down A square, then take A square minus 4A minus 5A. Prove that this is a, substitute these values, prove that this is a zero matrix, 0, 0, 0. Okay. So after verification of the Cayley-Hamilton theorem, then find out the A inverse. Means A square minus 4A minus 5y is equal to 0. Then multiply and throughout with A inverse. Means if we multiply with the A inverse, this becomes A minus 4I minus 5 into A inverse is equal to 0, is equal to 0, right? So from that find out the A inverse, then we'll get a inverse. Then from that find out A inverse, right? So this is a way to find out the characteristic equation and verification of the Cayley-Hamilton theorem and finding the A inverse, right? Right, then go back. Right? No, this is a, so after getting this one, so lambda is equal to minus 1 comma 5. So these are the roots, we got it. Now after that, next one, so this is a, we have to verify A satisfies the characteristic equation. So this one already I told. So then A square you have to calculate 9, 16, 8, 7. Now after that we have to verify the Cayley-Hamilton theorem, prove that this value is zero matrix. Then next find out the A inverse. Multiply with the A inverse stored, then find out the A inverse matrix like this. Then after that, by Cayley-Hamilton theorem, every square matrix satisfies the characteristic equation. So we got this is the equation. Now take the given polynomial, convert the given polynomial in the form of this one. In the form of this one plus A into plus 5i. Now substitute this value here, then we'll get the simple form. This is a polynomial. For directly we got linear. So this is a linear, means a degree is 1. No. So finally we converted the given polynomial in the form of the linear polynomial like this. Linear polynomial degree is 1, similar to the previous one, by applying the Cayley-Hamilton theorem. Right? This is a conclusion. So in this session we have discussed the following: problems on Cayley-Hamilton theorem on a square matrix, and remember that apply the Cayley-Hamilton theorem to the problem for finding the inverse of the matrix and higher powers of a matrices without using the routine methods.